Let's solve another thermodynamics problem requiring that an energy balance be applied to a closed system. A piston cylinder assembly contains water, initially a saturated vapor at 200 C. The water is cooled at constant temperature to saturated liquid. Kinetic and potential energy effects are negligible. Part A. For the water as a closed system, determine the work per unit of mass of water in kilojoules per kilogram. Part B, if the energy transfer by heat for the process is minus 1200 kilojoules, determine the mass of the water in kilograms. Well, let's lay out our storyboard for this problem. We have a piston cylinder assembly filled with water, and our dotted line indicates that the boundary of the system contains only the water molecules. The piston cylinder is not part of the system. The system undergoes a cooling process where Q is minus 1200 kilojoules. State 1, the state is given as a saturated vapor at 200, excuse me, a saturated vapor at 200 degrees C. And state 2 is given as a saturated liquid at 200 degrees C. On a TV diagram, that process would look like this under the vapor dome. We've got our vapor dome and a constant temperature line of 200 degrees C. State 1 exists as a saturated vapor, and it is cooled to a state where it exists as a saturated liquid, all at 200 degrees. We'll model this as a closed system with delta KE and delta P assumed to be 0. And it is a constant temperature process, and that as given and shown here on the TV diagram. And what we want to find is the work done, that small w, kilojoules per kilogram. And we want to find the mass of the water in the cylinder. Let's find the properties internal energy and specific volume for state 1. Now, state 1 is a saturated vapor at 200 degrees C. So we'll go to the saturated table organized by temperature. The first thing we're going to find is the saturation pressure is 15.54 bar. And because it's a saturated vapor, the specific volume V1 is going to be V sub G. And the internal energy at state 1 will be U sub G. And we have those values from the table. Now we want to find the same properties for state 2. We'll be at the same place in the table because it's still a saturated state at 200 degrees C, only now it's a saturated liquid instead of a saturated vapor. So the specific volume at state 2 will just be V sub F, and the internal energy at state 2 will be U sub F. And we have those values taken from the table. Well, now we want to find the work done, and that's small w, so we don't know the mass yet. And so we're looking for the work energy per unit mass, so kilojoules per kilogram. And we will notice that for this constant temperature process, because it all takes place under the vapor dome at the saturation pressure, it's also a constant pressure process. And we know that work, small w, is the integral of P to V, where that's small v. And we have previously integrated this expression and found that the algebraic equation is the pressure times the change in specific volume. So let's calculate the work. We have a pressure of 15.54 bar, and we have V2 minus V1. And our units now are bar cubic meters per kilogram. And we can convert that to kilojoules by noting that 1 bar cubic meter is equivalent to 100 kilojoules. And this gives us a work, that's small w, in other words, work per unit mass, of minus 196.2 kilojoules per kilogram. Now let's write the conservation of energy equation for a closed system, where we have ignored kinetic and potential energy. We can say that Q is equal to delta U plus W, and these are all capital letters indicating that all of these terms have units of energy. But I'm going to note that work, the capital W, is the mass times small w, where small w is energy of work per unit mass. So let's do some substitutions here. We have our original equation. Q is delta U plus W, so Q is delta U. I can rewrite delta U as the mass times the change in specific internal energy. And I can write W, capital W, as the mass times small w. Now I'll factor the mass out of the right side of this expression. I get Q is the mass times change in the specific internal energy, plus the work per unit mass, that's small w. Rearranging, solving for mass, I get mass is equal Q divided by the change in specific internal energy plus the work done per unit mass. Well, Q was given as minus 1220 kilojoules. I have values for U2 and U1, which came from the table. And we just calculated that the work was minus 196.2 kilojoules per kilogram. Solving this, I get a mass of 0.618 kilograms.